You know, we talk a lot about attention span these days.
Oh, yeah, constantly.
Usually it's about how ours is getting shorter. Like we're all turning into goldfish just scrolling through these 15-second videos. But for a long time in the world of artificial intelligence, the state-of-the-art models had an attention span that was, well, frankly, it was pathetic.
It wasn't just pathetic, it was mathematically capped. I mean,
Yeah.
we're talking about a hard limit that prevented the smartest models in the world, models that could literally write poetry in code, from reading anything longer than a pamphlet.
It's wildly ironic when you think about it. We had these incredible brains like BERT and RoBERTa that completely revolutionized how computers understand language. They were brilliant.
Right.
But if you handed them a novel or a long legal contract or a detailed scientific paper, they'd just choke.
Yeah, they would hit what we call the 512 token barrier. And that barrier wasn't just a suggestion, it's a brick wall.
So today, we're doing a deep dive into the paper that finally smashed that wall. We're looking at Longformer, the long document transformer. This is by researchers from the Allen Institute for AI, specifically Isbelthagi, Matthew Peters, and Armin Cohan.
And for you listening, this is really considered a foundational text in generative AI. This paper basically changed the math of attention from a quadratic problem to a linear one.
Which, if I remember my high school algebra correctly, is a very good thing when you're trying to save time and memory.
Oh, it makes all the difference in the world. It is the difference between a model that crashes if it reads more than a page and a model that can read thousands of words comfortably without even breaking a sweat.
Okay, let's unpack this, because before we get into the solution, the Longformer itself, we really need to understand the problem. Why couldn't AI read books? What was stopping a model like BERT from just turning the page and keeping going?
It all comes down to the core mechanic of the transformer architecture, which is self-attention. In a standard transformer like BERT, every single token, and you can think of a token as a word or part of a word, looks at every other token in the sequence to figure out the context.
So if I have a sentence with 10 words, word number 1 is looking at words 2 through 10.
Right.
And word number 2 is looking at word 1 and 3 through 10.
Exactly. It's an all-to-all connection. Everyone is talking to everyone. And mathematically, that operation scales quadratically. We call it O of n squared.
Give me a real-world analogy so I can picture this quadratic explosion. Because quadratic sounds a bit abstract until your computer catches fire.
Sure. Imagine you're at a cocktail party. If there are 5 people, everyone can easily have a conversation with everyone else simultaneously. It's loud but manageable. That's your short sentence.
Okay, 5 people manageable.
Now double the number of people to 10. The number of potential interactions doesn't just double, it quadruples. Now imagine you have 1,000 people in a massive banquet hall, and you require everyone to pay deep, focused attention to everyone else at the exact same millisecond.
The room explodes. Or at least everyone's brain melts.
Essentially, yes. In computing terms, you just run out of memory. That is exactly why BERT was capped at 512 tokens. If you tried to make the sequence longer, the computational cost would skyrocket so fast that modern GPUs just couldn't handle it. The matrix of connections gets way too big to fit on the chip.
So before Longformer came along, how are researchers actually dealing with this? If I wanted to feed a really long document, say The Great Gatsby, into an AI, what did I do?
You basically had 2 main hacks.
Yeah.
And I call them hacks because neither was an elegant solution at all. The first was truncation. You just cut the document off at 512 tokens.
So you say, here's a mystery novel, tell me who the killer is, but the AI literally stops reading at chapter 2.
Yeah, pretty useless for long tasks.
Right.
The second hack was chunking. You chop a document into 512 token pieces, feed them in one by one, and then try to stitch the answers together afterward.
It sounds like it could work in theory. You read page 1, then page 2, then page 3.
But here's the problem. You lose cross-partition information. Imagine the clue to the mystery is in paragraph 1, but the solution is in paragraph 50.
Oh, I see.
If the model processes them in separate chunks, it effectively has amnesia between chunks. When it's reading paragraph 50, it has zero memory of paragraph 1. It can't connect the dots. The attention mechanism is broken.
It's like reading a book, but having your memory wiped every few pages. You can understand the individual sentences perfectly fine, but you lose the plot entirely.
Precisely. You lose the global context. And that brings us to the promise of the Longformer. The authors designed a drop-in replacement for BERT that scales linearly with sequence length.
Linear scaling. So if I double the length of the document, the work only doubles instead of quadrupling.
Correct. This allows the model to handle documents of thousands of tokens easily. And they achieve this by redesigning how attention works. using 3 specific patterns. They basically told the model, you don't need to look at everyone at the party. You just need to look at the right people.
Okay, let's break these down because this is the core of it. The first one is called sliding window attention. How does that change our cocktail party scenario?
So instead of everyone trying to listen to everyone else in the entire room, imagine that everyone only listens to the people standing immediately to their left and right.
Okay, so I'm only paying attention to my immediate neighbors.
Right. In the paper, they define a fixed window size, so let's call it W. Each token only attends to W tokens on each side. So the computation becomes O of n times W. Since W is fixed, say 50 tokens, as the sequence length n gets bigger, the cost only grows linearly.
But wait, I see a flaw here. If I'm only looking at my neighbors, how do I know what's happening on the other side of the room? Like, if the clue is on page 1 and I'm on page 50, I'm not standing next to page 1 anymore. Isn't this just the exact same problem as chunking?
That is a great question, and it's where the layers of the transformer come in. Transformers are deep. They have many layers stacked on top of each other. So even if layer 1 only sees its immediate neighbors, layer 2 sees the neighbor's neighbors, and layer 3 sees the neighbor's neighbor's neighbors, it ripples out.
It's like a game of telephone, but an accurate one.
Exactly. This creates a receptive field that grows with each layer. By the time you get to the top of the model, say layer 12 or 24, you have a view of the whole input.
Right.
But that does create a new problem. It takes a lot of layers to see a really long distance. If the document is huge, the ripple might not reach the end fast enough.
Which brings us to their second innovation. They realized the ripple needed a boost, so they introduced the dilated sliding window.
Yes. Dilation is a concept borrowed from computer vision, actually. It's like having gaps in your attention. Instead of looking at tokens 1, 2, 3, and 4, maybe you look at token 1, then skip to 3, then skip to 5.
So you're widening your peripheral vision without actually focusing on more things.
Exactly.
Yeah.
You increase the receptive field, how far you can see, without increasing the computation cost. It allows the model to capture longer range dependencies with the exact same amount of effort.
It's kind of like skimming. You don't read the and. You skip a bit to get the broader context faster.
That's a very fair analogy. And the authors actually mixed these. In their experiments, they used different dilation settings on different heads of the attention mechanism. Some focused on the immediate details of the neighbors, and others focused on the long-range context using dilation.
So we have the sliding window for the neighbors and the dilated window for the broader view, but there's a third piece to this, and honestly, this seems like the most important one. The authors call it task-motivated global attention.
Oh, this is the secret sauce. Because you're right, sometimes sliding windows and dilation just aren't enough. Sometimes you do need to see the whole picture instantly, or you need every part of the document to look at one specific thing.
Can you give an example of when you'd need that?
Think about classification. In BERT, there's a special token called CLS at the very beginning. The job of that one token is to sum up the meaning of the entire document. Like, is this movie review positive or negative?
Right, so that one little token needs to know what everyone else is saying. It can't just talk to its neighbors, it needs the report from the whole room.
Exactly. If it only looked at its neighbors, it would only know the first sentence. So Longformer assigns global attention to that specific token. It becomes a VIP. It attends to every other token in the sequence, and crucially, every other token attends to it.
It's the host of the party again. Everyone looks at the host, and the host looks at everyone. But because it's only one person doing it, the room doesn't explode.
Yes. The math stays linear because the number of global tokens is very, very small. And they apply this selectively. For question-answering tasks, they give global attention to all the tokens in the question itself.
Oh, that's smart.
That way, as the model reads the document, every single word in the text can compare itself directly against the question. It doesn't have to wait for the information to ripple through the layers.
That makes so much sense. It gives the model a hint. It says, hey, no matter where you are in this long book, keep this specific question in mind.
And this inductive bias, giving the model a hint about the task structure, turned out to be essential. The ablation studies in the paper showed that without global attention, performance drops significantly on specific tasks. You really can't just rely on the sliding window. You need those anchor points.
Now, I want to get into the engineering for a second, because in the paper, there's this fascinating detail about a custom CUDA kernel. It sounds like something from a sci-fi movie, but reading between the lines, it sounds like it was a huge headache for the researchers.
Oh, absolutely. This is where theory meets reality. You can design a gliding window attention pattern on paper, and it looks great. The math works out perfectly. But implementing it on a physical GPU is a completely different story.
Because the standard tools just didn't work.
Right. Standard deep learning libraries like PyTorch and TensorFlow were built for full matrix multiplication, the dense quadratic kind. They assume everyone talks to everyone. They didn't have efficient support for banded matrix multiplication, which is the specific math you need for sliding windows.
So they had this great idea, but the tools to build it simply didn't exist.
They essentially had three bad options. One, write a loop in PyTorch, which is easy to code but painfully slow, like unusably slow. Two, use chunking, which is fast but uses way too much memory because it computes zeros that you don't even need.
So they chose option 3, build it themselves.
They used a compiler stack called TVM to write a custom C++ and CUDA kernel. This is really low-level programming. This allowed them to make the operation memory efficient and fast. Without this engineering feat, the Longformer would have just been a theoretical concept. It wouldn't have been practical to run at all.
That is some serious dedication. It reminds us that AI research isn't just about abstract math. It's about hardcore software engineering. So they build the architecture, they write the custom code, now they need to train it. And they didn't start from scratch, did they?
No, and that's a really smart move. Training a large language model from scratch is incredibly expensive. We're talking hundreds of thousands of dollars in compute time. So they started with a released RoBERTa checkpoint. RoBERTa is basically a robustly optimized version of BERT.
But wait, RoBERTa only knows how to count to 512. Longformer needs to go to 4096. How do you teach an old model new tricks without breaking it entirely?
They used a copy trick. RoBERTa has position embeddings learned vectors that tell the model this is the first word, this is the second word, up to 512. Longformer needed 4096 of these. So they simply copied RoBERTa's 512 embeddings 8 times.
They just copy-pasted. That sounds surprisingly crude for AI.
Essentially, yeah. And it worked because the local structure of language doesn't actually change much, whether you're at word 5 or word 5000. A noun is still usually followed by a verb. This preserved the learned knowledge from RoBERTa and allowed the model to converge very quickly. It saved them a massive amount of training time.
Okay, so they've got the model, they've initialized it, they trained it on books, Wikipedia, and long news articles. Let's talk results. Did it actually work?
It worked incredibly well. They tested it on character-level language modeling using datasets called Text8 and NWIC8. These are classic benchmarks in the field. Longformer achieved new state-of-the-art results. It could process sequences of up to 32,000 characters.
32,000 characters. That's a short story right there.
Exactly. But the real test was comparing it against RoBERTa on downstream tasks. Things like answering questions or classifying documents where the answer isn't just sitting in the first paragraph.
And how to do?
Longformer consistently outperformed RoBERTa on long document tasks. For example, on a dataset called WikiHop, which requires multi-hop reasoning.
Explain multi-hop for us, just to be clear.
It's when you need to combine two pieces of information to get an answer. Like, imagine I ask, who is the wife of the actor who played Star-Lord?
Okay.
You first have to find the fact Star-Lord is played by Chris Pratt. Then you have to find the second fact, Chris Pratt is married to Katherine Schwarzenegger. You have to hop between those facts.
And those facts might be pages apart in a single document.
Exactly. Standard models failed here because they chopped the document up. If fact A was in chunk 1 and fact B was in chunk 3, the model couldn't connect them. But because Longformer can see the whole document at once, it can make those hops instantly.
That's a huge upgrade. It's actual reasoning across a text.
They also looked at hyperpartisan news detection. This was a small data set with very long documents. Longformer excelled here too, proving it could adapt even when training data was scarce as long as it had the full context.
Now, there was one result that I found really interesting regarding a data set called HotPotQA. It seemed like Longformer didn't win everything, right?
Ah, yes, HotPotQA. This is a tough one. It's designed to be a highly complex reasoning challenge. Longformer set new highs compared to standard baselines, but it came in second to a very specific type of model called graph neural networks, or GNNs.
Why did the graph models win there?
Because HotPotQA requires very structured reasoning. Graph networks are explicitly built to link entities together in a web, kind of like a conspiracy theorist's string board. Longformer is just reading linearly. The authors admit that for tasks with heavy structure, explicit graph methods still had a slight edge at the time.
But Longformer was closing the gap significantly.
Yes, and doing it with a much simpler general-purpose architecture. It showed you can get 95% of the way there just by reading everything without needing to build a complex graph.
It's the difference between a specialist tool and a really powerful generalist.
Exactly. And speaking of generalists, we have to talk about LED.
LED. Like the light bulb?
No, LED stands for the Longformer-Encoder-Decoder.
Ah, okay.
Yeah.
Because up until now, we've been talking about understanding text, reading it. That's what the encoder does. But what if we want to write text?
That's where the decoder comes in. This is for sequence-to-sequence tasks like summarization. You read a long document and you write a short summary.
So they built a version of Longformer that could do this.
Yes, they initialized it from BART, which is
Oh.
another famous model, and expanded the position embeddings to 16,000 tokens.
16,000, that's huge.
It is. And the killer app was summarization of scientific papers. They tested it on the arXiv dataset.
Oh, perfect, because scientific papers are dense, long, and extremely painful to summarize manually.
Precisely. LED achieves state-of-the-art results, beating a competitor model called BERT. And there's a great chart in the paper Figure 3 that shows performance scaling linearly with input length.
So simply put, the more of the paper the model was allowed to read, the better the summary got.
It sounds completely obvious, right? But remember, previous models literally couldn't read the whole paper. They had to truncate it. LED showed that if you give the model the full 16,000 tokens, the quality of the summary just keeps going up. It proved that context is king. You can't summarize what you haven't read.
So looking back at this whole paper, what is the big takeaway for you? Because we started with models that had the memory of a goldfish, and we ended up with something that can digest an entire novella.
I think the synthesis here is that simplicity, when coupled with good engineering, usually wins. Before Longformer, people were building these massive Rube Goldberg machines, chopping documents, running complex retrieval systems, stitching things back together. It was messy.
And Longformer showed you don't need all that complexity.
Right. You just need a smarter attention pattern. You replace the quadratic bottleneck with a linear solution, sliding windows, plus a little bit of global attention, and suddenly the length limit effectively vanishes.
It really paved the way for the massive context windows we see today. I mean, now we have models claiming to read millions of tokens, but Longformer was the one that proved we could move away from just looking at sentences to looking at entire books.
It completely changed the unit of analysis. We stopped looking at snippets and started looking at documents as a whole.
Here's a thought to leave you with. The authors mentioned that for really complex reasoning, like in Hotpot QA, those structured graph neural networks still had a tiny edge. But Longformer showed that raw scale, just reading everything linearly, gets you almost all the way there.
It really raises the question, do we actually need to structure data? Do we need to tell the AI this is a graph of entities? Or if we can just make the context window infinitely long and the attention efficient enough, will raw scale eventually replace structure entirely?
Can brute force, or rather elegant linear force, replace the need for complex logic structures? That is definitely something to mull over next time you're struggling to finish a long book and wondering if you missed a crucial plot point on page 40.
Or, you could just ask an AI to summarize it for you.
That's exactly the plan. Thanks for joining us on this deep dive into Longformer. We'll catch you on the next one.